lacuna. Let me first introduce the exponential function, which is probably one of the most important functions from all of mathematics. Without further ado, let me just state a theorem. There is a unique function f from R to R with the following properties. Number 1, f of 0 is equal to 1. Number 2, f prime of x equal to f of x for all x in R. So there is a unique function which takes the value 1 at 0 and whose derivative is itself. Proof. Now that we are masters of power series, this is a fairly easy thing to do. Define f of x is equal to summation n equals 0 to infinity x power n by n factorial. Okay. Now the question is, if this series converges, then what is its derivative? Let's first assume that the series converges. Let's compute its derivative. Well, f prime of x, we know that if a power series converges, then in the interval of convergence you can do term by term differentiation. So this will be summation n equals 1 to infinity n x power n minus 1 by n factorial, which you can just see is just summation n equals 0 to infinity x power n by n factorial. Okay, and it's also clear that f of 0 is equal to 1. That is also trivial to see. So all we have to show is that this function f converges at every point of the real numbers. Now there are several proofs of why this series converges. I suggest that you spend a nice monsoon afternoon contemplating various proofs. Let me give the simplest, not the one that uses the least number of tools, but the simplest according to me. Apply ratio test. Well, what do you get when you apply ratio test? You get x power n plus 1 by n factorial, n plus 1 factorial divided by x power n by n factorial. Okay, well, what happens to this? You just get n factorial and n plus 1 factorial. The n factorial part will get cancelled. You will get x divided by n plus 1. Okay, which of course converges to 0 as n approaches infinity for any fixed x. Therefore, for each x, the ratio test tells you that it is convergent. Therefore, the power series converges at every point of the real numbers. In other words, the radius of convergence of the power series is infinity. Okay, so we have shown existence. Well, what about uniqueness of this power series? Well, what you do is let g be another function that satisfies 1 and 2. We have to show that f is equal to g. How are we going to do that? First, we will show that any function that satisfies 1 and 2 is never 0. Claim if g satisfies 1 and 2, g of x is not equal to 0 for all x in R. Well, why is this the case? Well, because look at g of x times g of minus x. Look at g of x times g of minus x. Look at this new function, call it h of x. Differentiate this h. Well, by product rule, what do you get? You get g prime of x times g of minus x minus g prime of minus x times g of x. Okay. I hope I have done the differentiation correctly. Well, g prime, one moment, this is just, this I have to be 100% precise. Uh, this is just, let me just clarify, because there might be a bit of confusion if I write it like this. This is derivative of g evaluated at the point x. So I'm writing bar and x at bottom to sort of say that I'm first taking the derivative, then evaluating at the point x, times g of minus x. I'm just applying the product rule. Then I have to differentiate g of minus x, which by chain rule is just minus g prime. So that's why there is a minus sign. So it's minus g prime, but this time evaluated at minus x. Evaluated at minus x into g of x. Okay, but we know that g prime is just g, right? So this is just g of x, g of minus x, minus g of minus x, g of x. Okay, so the reason why I introduced this notation of evaluating at the point x is to make sure that when I write g prime of minus x, you don't think it is, oh, I have to differentiate the function g prime of minus x, which is minus g prime of minus x, which will sort of lead to confusion. So that's why I'm introducing this notation. Now this everything just cancels and you get 0. Okay, so what does this tell us? Well, this tells us that h of x is a constant, is some constant, let's say k, which means g of x into g of minus x is just this constant k. Okay, which means, and wait a second, we can even determine what this constant is. Setting k equal to 0, setting x equal to 0, we get k equal to 1. Okay, so g of x into g of minus x is 1, which means g of x is never 0. Okay, so this proves the claim that any function that satisfies properties 1 and 2 is never 0. Now what we do is consider f by g. Consider the function f by g. F and g are both functions that satisfy the properties 1 and 2. Now differentiate f by g. Differentiate this. Okay, now I'm not going to bother doing the derivative. Just by the fact that f prime equal to f and g prime equal to g, you will immediately conclude that the derivative is 0. Okay, because the numerator will have fg prime minus f prime g. So this will be 0. So what this shows is that f by g is some constant k. So f is actually k times g. Now that means f of 0 is k times g of 0, or in other words k is equal to 1. So we have shown that f is identically equal to g. Okay, so uniqueness is established. Uniqueness is established. We have also got a useful fact about this function f, which came out in the proof, the fact that f of minus x is just f of x inverse. Okay, please keep this in mind. This will be very, very useful. Okay, now we already know that f of x is not 0 for all x. That is also something that came out in this proof. And we also know that f of 0 is equal to 1. Therefore, by intermediate value theorem, because f is of course a continuous function, it's in fact given by a power series, so it's a smooth function. By intermediate value theorem, f is never negative. F is never negative. Okay, so the function f, whose existence and uniqueness we have established in this theorem, also is always a positive function. Okay, now f prime of x is just f of x, right, which means derivative is positive for all x, right? The derivative is a positive function. This means f is a strictly increasing function, which we have seen in the various theorems that we have established in the part on calculus, differentiation, the part on differentiation. Okay, so f is a strictly increasing function. Not only that, f double prime is also equal to f prime is also equal to f is also positive, which just goes to show that f is convex upwards, Okay, putting all of this together, we get the familiar graph of the exponential function. At 0 it is 1 and the function is sort of going to look like this. Okay, so I have drawn it badly. It should actually be more steep. So let me try to rectify. I will not say I will rectify it for sure. Something like this. It should be steeper. This is the roughly the graph of the exponential function, as we can see from all the facts that we have. The fact that it's strictly increasing, it's convex upwards, at 0 it's 1, so on and so forth. Okay, now another property of the exponential function that you are familiar with is f of x plus y is f of x times f of y. Okay, now you will notice that I am going to prove everything from the two properties in the previous theorem, that f of 0 is equal to 1 and f prime is equal to f. So what I'll do is fix a and consider g of x to be f of a plus x. Okay, now differentiate. G prime of x would be just f of a plus x times what is inside, it's f prime at a plus x times the derivative of what is inside by chain rule, but the derivative of what is inside is just 1. So g prime of x is just f prime of a plus x. Again, for clarity, let me just write f prime evaluated at a plus x, which is just f of a plus x, which is equal to g of x. Okay, now if you go through the argument that we gave to show that if there is another function g that satisfies both 1 and 2, then we must have that f is k times g, right? And then we used property 1 to show that k is 1. So here we have a function g that just satisfies property 2, the fact that g prime equal to g. With that, just that property alone, we will be able to show that f of x equal to k times g of x. That we will be able to show. We will not be able to show that this k is equal to 1 because we don't know that g of 0 is equal to 1, but this is a start. Now substitute x equal to 0 and let's see what happens. In the previous proof, k dropped out to be 1. Substitute x equal to 0. So what you get is 1 is equal to k times g of a, right? Because we have substituted x equal to 0 and g of x is just f of a plus x. So sorry, this should be f of a, not g of a. This should be f of a. Okay, fine. Which just goes to show that k is nothing but 1 by f of a. Okay, that means what we get is f of x is equal to g of x by f of a, or in other words, g of x is f of x times f of a, which just goes to say that f of a plus x is f of x times f of a. Okay, hence proved. Okay, so we ultimately wanted to show that f of x plus y equal to f of x plus f of y. We have just fixed y to be a and proceeded with this argument. So ultimately we have got the product property of exponential functions. Now inductively, we can now using this fact, using this fact, we can show that f of n times a, n in the natural numbers, is nothing but f of a power n. Okay, this is certainly true when n equal to 1. When n equal to 2, we just say f of a plus a is just f of a squared. That is what the previous result is saying. Inductively, it's easy to show this. Okay, now set e to be equal to f of 1. Okay, define e to be f of 1. We have already analyzed this number in a module, in an earlier module. In particular, we have shown that this e is actually an irrational number. We have actually shown that this e is an irrational number. So what our theory so far says is that e power n is nothing but f of na. Excellent. We also know that f of minus na is e power minus n. This also follows from the fact that f of minus x is just f of x inverse. Because of that, we get f of minus na equal to e power minus n. So what we have got is, at least for certain quantities, just a moment, this is not, there's no a in these equations. It's just, sorry about this, but e power n is f of n and f of minus n is e power minus n. So at least for all integers, for all x in z, we have this e power x is equal to f of x. Okay, so by analogy, we represent f of x by e power x. Okay, note very carefully what is going on. I am not saying that the function f, whose existence and uniqueness we have proved, is actually exponential but with base e power x. That's not what I'm saying. We have not yet defined what power x means when x is just any real number. We know how to define exponential taking power to a natural number. We also know how to do it for a rational number, but we don't yet know how to do it for a real number. We have just informally defined it using logarithms as and when needed in earlier modules, but the purpose of this particular set of modules is to make all that rigorous. Okay, so by analogy, we are representing f of x by e power x. That's all. Okay, that's all we are doing. Now, I'm going to leave you with an exercise. Show rigorously just using e power x equal to summation n equals 0 to infinity x power n by n factorial, that limit x going to infinity e power x by x power n is equal to infinity. So for each fixed n. We have already established this, but I want you to show this just by using the power series expansion. Okay, just by using the power series expansion. Okay, so these are all the properties of exponential that will be needed in this. I mean, that's not just needed, that's usually needed in practice. The exercises contain more properties of the exponential function that you can prove either directly from the power series expansion, or better, just by using properties 1 and 2 in the big theorem we proved in the beginning of this module. This is a course on real analysis, and you have just watched the module on the exponential.